Imagine water that doesn't just boil, but acts like a ghost, passing through solid rock while dissolving industrial steel like sugar. This is the supercritical realm, a physical state where the line between liquid and gas completely vanishes. Normally, we think of water as life-giving and harmless, but at 374 degrees Celsius and crushing pressures, it becomes a universal solvent so aggressive it can eat through the very pipes meant to contain it. Engineers at the MIT Spring Symposium recently unveiled a breakthrough that finally tames this violent fluid. It's a drill bit designed to survive the impossible, and it's about to change how we power the planet.
To understand the drill, we first have to understand the water. Below the critical point, water molecules are held together by strong hydrogen bonds, but as heat and pressure climb, those bonds start to break down. Once you cross the threshold of 22 megapascals, the water enters a supercritical state. It has the density of a liquid but moves with the low viscosity of a gas, allowing it to penetrate the tiniest pores in solid granite. In this state, the water's dielectric constant drops significantly. It stops acting like the water in your tap and starts acting like an organic solvent, capable of dissolving minerals and metals that are usually indestructible. This chemical shift is what makes supercritical geothermal so difficult. In standard drilling, water cools the bit, but here, the water is a corrosive acid that attacks the drill's structural integrity. The engineering challenge is a paradox. We need to use this water to carry massive amounts of energy, but we have to build a machine that can survive being inside its own fuel source. If we can solve this, we unlock a power source that is 10 times more energy dense than traditional geothermal. It's the difference between a campfire and a jet engine. The key is a phenomenon called hydrogen embrittlement. At these temperatures, hydrogen atoms from the water actually wedge themselves into the metal's crystal lattice, making it as brittle as glass. You could have the strongest steel in the world, and under these conditions, it would simply shatter the moment it hit the rock. This is why standard oil and gas tech ails instantly in the supercritical zone. To move forward, the engineers at MIT had to look beyond traditional metallurgy. They needed to find materials that don't just resist the heat, but ignore the chemistry of the water entirely. This brings us to the breakthrough unveiled in March 2026, a drill bit that combines the hardness of diamond with the chemical immunity of specialized refractory coatings. It's a masterpiece of material science that turns the world's most aggressive environment into a playground for energy production. And the secret lies in how they shield the metal core. But before we look at the coating, we have to see what this bit is actually fighting against: the hardest rock on Earth, under the weight of 5 miles of crust. Drilling through granite is usually like trying to cut through a brick with a plastic knife. At 5 miles down, the rock is so hot it becomes ductile, meaning it flows back into the hole as fast as you can drill it. To win this fight, the MIT team utilized a core made of nickel-based superalloys. These are the same materials used in the hottest parts of jet engines, designed to maintain their strength even when they are glowing white hot. But even superalloys aren't enough. In supercritical water, they would still corrode. The genius part is the refractory coating, a microscopic suit of armor applied one atom at a time. The coating is primarily composed of tantalum and niobium. These elements have melting points over 2400 degrees Celsius. To them, the 374 degrees supercritical water feels like a cool breeze. These coatings are applied using a process called physical vapor deposition. In a vacuum chamber, the refractory metals are turned into a plasma and blasted onto the drill bit, creating a bond that is virtually unbreakable. This creates a chemical ghost layer. The supercritical water sees a ceramic-like surface that it can't dissolve, while the superalloy core provides the mechanical strength to handle the torque of drilling. But a drill is only as good as its teeth. For the cutting edges, MIT used polycrystalline diamond compacts, or PDCs. These are synthetic diamonds grown in massive presses at pressures that mimic the Earth's interior. Usually, diamonds are vulnerable to heat. They can actually turn back into graphite if they get too hot in the presence of oxygen. But in the deep, oxygen-free environment of a geothermal well, they are the ultimate weapon. These diamond teeth are brazed onto the bit using a specialized gold-nickel filler. It sounds expensive, but when you're drilling a multi-million-dollar hole, you want the best materials humanity has to offer. The engineering doesn't stop at the materials. The bit's geometry is designed to use the supercritical water itself. Tiny nozzles blast the fluid at the rock face, using the water's high density to help erode the granite.
This is hydromechanical drilling. The diamond teeth crush the rock, and the supercritical jets clear the debris instantly, preventing the bit from getting clogged in this sticky, hot environment. It's a perfectly synchronized dance of physics and chemistry. The water that wants to destroy the tool is actually being used as a weapon to clear the path.
To manage the heat, the bit also features internal cooling channels. Even though the surrounding environment is 400 degrees, the fluid flowing through the center is kept just slightly cooler to maintain the bit's structural stiffness. This is basically a liquid-cooled computer, but instead of a CPU, it's a 500-pound rotating hammer eating its way through the crust of a planet. The result is a tool that can stay down whole for hundreds of hours, whereas previous designs would melt in minutes. Now it's time to see where this beast is being unleashed. All this lab-grown tech is being put to the ultimate test at the Utah Forge site. This isn't just a research lab, it's a massive industrial proving ground where engineers are drilling miles into the Earth's crust. The logistics are staggering. They aren't just lowering a drill, they are managing a high-pressure plumbing system that spans kilometers of vertical rock. Every component must withstand the weight of a mountain. At these depths, the pressure is so high that the steel drill pipe itself behaves like a wet noodle. Managing the vibration and torque from 5 miles away is like trying to perform surgery with a 50-foot straw. The Utah site is unique because it uses enhanced geothermal systems. They don't look for existing hot springs. They create their own by fracturing the hot granite and pumping water through it. By using the new MIT bits, the team can reach depths where the rock is naturally hot enough to create supercritical steam. This turns the Earth itself into a giant high-efficiency boiler for carbon-free power. This is a closed-loop system. The water is pumped down, heated by the rock, used to spin a turbine, and then sent right back down to do it again. Zero emissions, 24/7 power. The hardware at the surface is just as impressive. To handle supercritical fluids, the valves and turbines have to be made of the same exotic alloys as the drill bit. We're talking about pressures of 3,000 psi and temperatures that would melt lead. The engineering margin for error is zero. One failed seal could result in a catastrophic release of energy, but the payoff is worth it. A single supercritical well can produce as much electricity as 10 traditional geothermal wells, making it finally competitive with fossil fuels. The most exciting part, this isn't limited to Utah. Hot rock exists everywhere on Earth if you drill deep enough. With these new bits, we can turn any spot on the map into a power plant. Imagine a world where energy is no longer a matter of geography. No more oil fields, no more coal mines, just the heat of the planet itself, tapped by a drill bit that refuses to die. It's the ultimate engineering victory, using the very materials that make our modern world to unlock a source of energy that will last as long as the Earth itself. The MIT Spring Symposium of 2026 will be remembered as the moment the supercritical barrier was finally broken. We've gone from fearing the universal solvent to harnessing it. Next time you flip a light switch, think about the miles of rock and the impossible chemistry happening beneath your feet. The heat of the Earth is finally within our reach. We are no longer just living on the surface of a planet. We are finally learning how to use the engine that runs it. And that engine is just a few miles down.